In this session, we'll be again looking at an algorithm to design a kernel for the vertex cover problem. So what's new now is, first of all, we'll get a kernel where the number of vertices is 2k. Compared to, remember yesterday we got a kernel with k square vertices. So it's of course an asymptotic improvement with respect to the kernel size. Moreover, what is more important is the way we get that kernel. We'll use a linear program for vertex cover, like a solution, we'll write a linear program for vertex cover, solve it, and based on the values that an optimum solution to the linear program that we get, based on that we'll design reduction rules. So I think, that's what I want to highlight for today's talk. How can one use linear programs to design kernels? So you have seen how can one use linear programs to design approximation algorithms, for example, for vertex cover, I believe, right? So today we'll see how to design kernels, in particular a kernel for vertex cover using linear programming, okay? So let's start. So again, the problem is vertex cover, we all know it, I'll not write it. We all know what a linear program is, right? You've done it in last class. And you all have also seen a linear program for vertex cover, right? So given a graph G, for each V in Vg, let's say we have a variable xv, and we write a program, the linear program is, you want to minimize the sum of these values subject to constraints, which are, what is the linear program for vertex cover? Xi plus xj is greater than or equal to 1 for every h ij, right, in the graph. So let me just use uv here, like I'm denoting the vertices with u and v. So for every edge uv in the graph, we have these constraints, right? If suppose I wanted to write a linear program that exactly solves vertex cover, I would want that all the variables take values between 0 and 1, right? And that's what is called integer linear program for vertex cover, right? But what we know is that this problem is NP hard. So if we have these constraints, which are integer constraints, then it makes the problem NP hard, and hence we can't find an optimum solution to this LP if we have linear constraints. So for example, for designing approximation algorithms, you saw that if we can relax these constraints in the sense that we can allow these values to be fractional between 0 and 1. But now, of course, when you get fractional values, that the values doesn't really correspond to a vertex cover in the graph. But as you saw in approximation algorithm, we can do something with these fractional values and try to get some approximate, like you tried to get some approximate vertex kernel. Again, here also, so what we'll do is, we have this linear program with relaxed values, so non-integer, it could be non-integer values. This is a linear program, and we know any linear program can be solved in polynomial time, right? And when I say solved, meaning we can find a set of values to these variables, xv variables, that satisfy these constraints and which minimizes this value. So what we'll do is, we've written this linear program, we'll run the LP solver which solves this LP and outputs us these values, these xv values that satisfy these constraints and minimizes this function. And then based on the values, we'll design reduction rules, okay? And we'll prove that those reduction rules are safe, we can actually apply them and get an equivalent instance. And after the application of the reduction rule, the number of vertices in the graph is bounded by 2k. So that will be first half of the talk. In the second half of the talk, so the first step of this algorithm is solving this LP, right? So right now I said that we know that LP can be solved in polynomial time, that there are a lot of methods for doing it. And I don't even know the details of those methods because most of them are very complex. But there are polynomial time algorithms that given an LP solves it, okay? But for this problem, for the vertex cover problem, we'll actually see a very simple algorithm that solves this LP. That means an algorithm that outputs a set of these xv values which satisfy these constraints and minimizes this value, okay. So that will be the second half of the talk. As of now, we can assume that someone has actually solved this LP for us. In other words, they have given us these xv values that satisfies these constraints and minimizes this value, okay. So let's start. So henceforth throughout the lecture, whenever I say LP VC of G, I mean this linear program that I've written. So this is the linear program for vertex cover for G. So with respect to G, for each vertex there are these variables, and for every edge there are these constraints, okay. And so we have this linear program for G, and someone has given you an optimum solution to this value. So basically someone has given us values, let's say AVs are the values for the variables XVs, and these values corresponds to an optimum solution of this LP. That means these values satisfies these constraints and minimizes this function, okay. So we have these values, they can be found in polynomial time. So what can we do with these values is what we are gonna see. So based on these values, let us partition the vertex set of the graph into 3 parts, and I'll tell you what these 3 parts are, okay. So basically, look at all the vertices which get value less than half, okay. Let's call this set of vertices V0. Look at all the vertices that gets value greater than half. Let's call this set V1. And let's call the remaining vertices, which are the vertices that get value equal to half. Let's call this set V half. V0, V1 and V half form a partition of the vertex set of the graph. Every vertex is in one of these parts, right? So the core of the algorithm lies in the next theorem, which we'll prove, which was given by these two people, Nimhauser and Trotter. So this is a theorem given by Nimhauser and Trotter, and what this theorem states is the following, which is the most interesting part. So what this theorem says is that there is, okay, or let me just say it and then I'll write it. It says that there is always a minimum vertex cover that picks all the vertices of V1 and that doesn't pick any vertex from V0. So it says there is a minimum vertex cover of G that picks all of V1 and none from V0. We'll prove this, but at least if we prove this theorem, then this sort of will give us some reduction rule, right? Because if we know that there is always a vertex cover, minimum vertex cover, that picks all of V1, then we can just look at the vertices of V1, basically look at the vertices which get this value at strictly greater than half in this when we solve this LP, and we can just delete them from the graph and decrease the budget by the cardinality of V1, right? At least. And then of course we have to prove that, okay, once it's done, why is the size small and all, but at least we know that if we prove this, we are getting close to, we'll be close to getting some reduction rule, okay? So, but again, we'll come to it later. Let's look at the proof of this theorem first. So let's look at the proof. To look at the proof, let us observe certain values about, certain properties about these sets, V0, V1 and V0, okay? So let's look at all the vertices in V0. Let's look at all the vertices in V1 and let's look at all the vertices in, okay, while they're setting it up, what do you, like, look at all the vertices in V0. When do we put a vertex in V0? When it gets value strictly less than half, right? So look at any two vertices in V0. Is it possible that there is an edge in the original graph between these two vertices? Exactly. So if there are two vertices, both of which get value strictly less than half in any optimum solution to this LP, then they can't have an edge between them, because if there was an edge between them, the value sums should add up to 1, right? So what we observed is that V0 is actually an independent set in the graph. Now look at any vertex in V0 and any vertex in V half. V half were the vertices which were getting value exactly half. Can there be an edge between a vertex of V0 and a vertex of V half? Same, because they will not add up to 1, right? So this is one structure that we observe based on the values, right? Okay, so now suppose, so we know V0 is an independent set, and all the neighbors of V0, where are they lying? They can't lie in V half, they can't lie inside V0, where are they lying? In V1. So all the neighbors of V0 are in V1, okay? So for example, let's forget about the size, but for example, if I give you any vertex cover, okay, which contains V0, I mean, you can always give me a vertex cover that does not contain anything from V0. You don't pick anything from V0, rather pick all of V1. Okay, let's quickly write it down, what we said here. So we observed that V0 is an independent set. There is no edge between V0 and V half. These sort of edges are not present, right? So the neighborhood of V0 is entirely contained inside V1, right? All I'm saying is, if size is not an issue for you, you can always give me a vertex cover that does not pick anything from V0 and pick the whole of V1. So let's see, so what we actually want to do is the following. Suppose someone came and gave us a minimum size vertex cover in the graph. So suppose S star was a minimum vertex cover of G, okay? We want to prove that there is always a minimum vertex cover that takes the whole of V1 and none of V0. That's what we want to prove, right? So we like, okay, fine. Suppose someone gives us a minimum vertex cover of G. What we do is we try to construct another vertex cover from S star in the following way. We delete all the vertices of V0 from S star and take the whole of V1 into S. Okay. Clearly S is a vertex cover of G, right? Because S star was a vertex cover. Now from S star we have deleted V0, right? But we know that all the edges incident on V0 were in V1, and we have taken the whole of V1. So S is definitely a vertex cover, right? If suppose we can prove that the size of S is at most the size of S star, then have we proved the theorem? Because I have given you a vertex cover of G whose size is at most the minimum vertex cover, and which contains the whole of V1 and nothing from V0, right? So basically the rest of the proof is proving that this S that I have constructed like this has size at most S star, okay? So let us write more precisely what is the size of S in terms of the size of S star. So what is the size of S? How have we constructed S? We took all the vertices of S star into S. From there we deleted all the vertices V0. Basically we deleted all the vertices of V0 that were in S star, right? And we added all the vertices of V1 that were not already in S star, right? So what we have added is what we have added is V1 minus S star, right? This is the size of S. So if I have to prove that S is at most S star, it is enough to prove what? S star intersection V naught is? Yeah, well, I mean, it's enough to prove that it's greater than equal to V1 minus S star, right? Because if what I'm subtracting is more than what I'm adding, then the resulting thing is at most S star. Okay, so this is what we'll prove now. Okay, and the way we'll prove is the following. We'll say that, okay, if this is not the case, maybe the S that you have constructed already has this property that, or maybe the S star that I gave you already has this property that the S star intersection V0 was greater than equal to V1 minus S star, in which case we are done, in which case the S that I've computed will have size at most S star. So maybe this is already done, but if this is not the case, then we'll prove that if this doesn't happen, then this LP solution that you have given to me, these AV values that you claimed were an optimal solution to this LP, will prove that if this does not happen, then this is not an optimal solution to the LP. And how we'll show that is, we'll say that, okay, if this doesn't happen, then we'll give another solution to this LP, which is a feasible solution and whose value is smaller than this value of this solution that you've given me. So that way we would have proved that this is not an optimal to begin with. Or in other words, if this does not happen, then this is not optimal. Or in other words, if this is optimal, then this will always happen. Okay. So let's see. So we have to prove this. So basically we are proving this by contradiction. Suppose this does not happen. So if this does not happen, that means S star intersection V0 is strictly less than V1 minus S star, right? So because of this, we'll prove that, this is not an optimum solution to this LP. So we have V0, we had V1 and we had V half. And we are in the case where this value is strictly less than V1 minus S star, right? So using this, we want to say that, okay, then if this is, we want to say that if this is the case, then this set of values is not an optimum solution to the LP. Right? This is what we want to say. So to do so, let me give you another assignment, like another solution to that LP. Okay, so I'll give you another assignment to the variables of that LP. Firstly, I'll tell what that assignment is. Then we'll prove that that is indeed a feasible assignment to that LP, and then we'll prove that like the value of this assignment, that means the summation of all these values, is strictly less than the summation of all these AV values, thereby proving that AV was not an optimal solution. Okay. So for that, to begin with, let me first give you what that assignment will be. Okay. So now what I'm going to give you, I'm going to give you another assignment, let me say A prime V for every vertex in V. Okay. To do so, okay, see, the idea is the following. What I'll be doing is, there are, let's say this is this set of V0 vertices which S star was picking, and this is the set of V1 minus S star vertices that the S star was not picking. What we'll do is, we'll give another assignment. We'll change the assignment of these vertices and these vertices. I mean, intuitively, what we'll do is, we'll choose a certain number that's small enough and that works fine for all other purposes. We'll choose a certain number and we'll subtract it from all the look at the values that look at the AV values of these vertices. We'll subtract a certain number from these AV values and we'll give that number as the new assignment for these AV values. So basically, for all these values, I'll give some smaller assignment. Like what if AV was, for example, assigning this 0.6, I'll assign it, say, probably 0.8 or 0.9, something smaller. And for all the vertices in V0 intersection Vs, for all these vertices, I'll be assigning something strictly larger than what AV was assigning. For example, if AV was assigning it 0.4, I'll probably assign it 0.41 or something like that. And we'll do it in a way such that everything fits in. So what will happen is, for all these vertices, I would have subtracted a certain value from its original assignment, and from all these vertices of V0, we would have, so from all these vertices of V1 minus S star, we would have subtracted a particular value from the original assignment, and for all these vertices in V0 intersection V star, we would have added a particular value, okay. And now, because this set, this V0 intersection S star set is strictly smaller than V1 minus S star set, then what would happen is, what we would have subtracted would be more than what we would have added. Because we subtract things from V1 minus S star, we added things to the vertices of V0 intersection S star. So what we subtracted would be more than what we added, because we'll be subtracting or adding the same value from every vertex. Okay. So this will be the new assignment. We'll of course prove that it is feasible, but we'll prove that it is feasible, but note that this assignment will definitely be smaller than the original assignment. So when I look at the sum of this new assignment, sum of this assignment on all the new vertices, so all the other vertices will get the same assignment as AV, whatever AV was giving it. These new vertices get a changed assignment. So at least clearly this new assignment will have, when I've summed up the values given to the vertices by this new assignment, they'll be strictly less than whatever the sum we were getting corresponding to AV. So this is definitely a smaller assignment. If I prove that it is also a feasible assignment to LP, I have proved then that AV was not an optimal assignment, because I proved that there is an assignment that gives us a smaller value. Okay, so that's the proof. So let me now start, let me write it down formally what that assignment is. So let me first define that number that I'll be subtracting from every vertex or adding to the other vertices. So I'll be subtracting something from this set and adding something to this set, right? Let me first define that number, and I'll just define it. We'll see why we have defined it like this once we reach the end of the proof, because that's where we'll need that number to be defined that way. So we'll understand only why we have defined this number that way only when we reach there. Okay, so as of now, let me just write it down how we are defining it. So I'm going to define a number epsilon. And what is epsilon actually? So look at the AV values of all the vertices in V0 and V1. So whatever AV, look at whatever values these vertices and these vertices were getting with A, okay? So note that all the vertices here were getting a value of strictly less than half, and all the vertices here were getting a value of strictly greater than half, right? So let me just, for ease of understanding, project these numbers on a number line. So let's say this is half. There were the vertices of V0, they were getting some values here, right? The vertices of V1 were getting some values here. Okay. I choose epsilon to be that AV value which is closest to half. So basically, if for every vertex in V0, you look at its AV value and mark it here on a number line, look at the vertex which is closest to half. It could either be this vertex or this vertex, depending on this distance and this distance. Okay. And suppose this distance was smaller, then I'm calling this distance to be epsilon. Formally speaking, epsilon is the min of the absolute the AV value minus epsilon, min over all vertices in V0 minus V1. So you look at all vertices in V0 union V1, and basically look at the vertex whose value is closest to half, okay? And look at the difference between that value and half, and that is what is epsilon for me. Why we have chosen it, we'll see why we have chosen it towards the end of the proof. So this is epsilon, okay. Now I'm ready to give you a new assignment that I claim is feasible and has values strictly smaller than AV, okay. So that assignment is as follows. So I'm giving this assignment A prime V. For any vertex V, if V belongs to V0 intersection S star, then I give it value AV minus epsilon. Yes, sorry, plus epsilon. And for vertices in V1 minus S star, I give it value AV minus epsilon. And for all the other vertices, I give it value AV. This is the new assignment. I've fixed it. Okay. So let us first prove that. So of course, it's not clear why is this a feasible assignment to the LP, as in why does this assignment satisfy all the LP constraints? It's not clear. We'll prove it. But even before that, let us see that is it clear that this always holds? Because we are in this case, right? Because if you look at the sum of AVs, if you look at the sum of these AV primes, for all other vertices it will be AV. For the vertices of V0 intersection S star, I have added plus epsilons, and for all the vertices in V1 minus S star, I have subtracted epsilon, and the set V0 intersection S star is strictly smaller than this. So what I've subtracted is strictly more than what I've added. So this is always true, right? Now if I prove that this set these values, okay, if I prove that these values are a feasible solution to the LP, if we prove that this is a feasible solution to this LP, then are we done? Because if this is a feasible solution, then we have a contradiction that to begin with AV was a feasible solution. So this is a contradiction to the fact that this happens, right? And if this does not happen, that means this happens. If this happens, then we've already proved the claim. We have already given an S, its size is at most S star, and which is the vertex cover, and S star was a minimum vertex cover. So we have actually proved that there is always a minimum vertex cover that picks all of V1 and nothing from V0, right? So now the aim is to prove this, that the new assignment that I've given is a feasible solution to the LP problem. Okay, so for this, what do I have to prove? It will be feasible if it's a feasible solution, meaning if it's a feasible solution. So remember, if it's a feasible solution, we have to show that it satisfies those two constraints in the LP. What are the two constraints? First is for every edge UV, A prime U plus A prime V should be greater than or equal to 1, and also that all these A prime V should be in the range 0 and 1. So let us first prove, so basically we have to prove this and this. Let us first prove this. Is it easy to see that all the newly constructed A primes will be in this range? Why? Like for example, I have added epsilon to two vertices of V0. Added epsilon to vertices of V0. V0 had values half, yes. And epsilon is at most half, the way we have defined it, right? Right. So epsilon is at most half, and so and originally these AV values for example V0 were strictly less than half. So at least all these sort of values will be between, they'll not shoot up. So if AV was between 0 and 1, this will also remain between 0 and 1. Similarly, these values, can this go below 0? Of course, they'll not go above 1 because AV was not above 1. So can this go below 0? Why? Yeah, because AV was greater than half and epsilon is less than half, right? Yeah, so that is important. So this is one reason that we have to define epsilon carefully, that it should not be more than half at any point of time. Okay, so clearly we know that for every V this holds. Now we have to prove that for any edge uv in the graph, a prime u plus a prime v is greater than or equal to 1. Right? Let's see why this holds. Now for this, let us again use this picture. Let us look at all the kinds of edges possible. We know that there are no edges like this, right? We know that there are no edges inside it, right? So where are the edges? Look at any edge that is inside V12, okay? Does this hold for these kind of edges that are inside V12? Does this hold for these kind of edges that are inside V12? Yeah, because a prime of V, u and a prime of V for these kind of edges is the same as the previous thing, and previous thing was a feasible solution. So definitely this holds for these kind of values. So now what can you say about these kind of edges? An edge between a vertex of V0 intersection S star and an edge between vertex of V1 minus S star. So what will be, like, look at an edge whose one endpoint is in V0 intersection S star and the other is in V1 minus S star. For such an edge, for example, let's say U is in this set and V is in this set. For such an edge, what will be A prime of U? It is AU plus epsilon, right? And what is A prime of V? So what is A prime U plus A prime V? So if AU plus AV was greater than 1, this is also greater than 1, right? So these sort of edges are also taken care of. Okay. Now, can there be such an edge in the graph from V1 minus S star to, like, exactly the thing that I have drawn, V1 minus S star to the set outside this V0 minus S star, this kind of an edge? Can there be this kind of an edge? For here, observe that S star was a vertex cover of edge. So every edge has at least one endpoint incident on S star. And the edge that I am talking about here, this endpoint of an edge, this is definitely not an S star because these are the vertices of V1 that are not in S star. And these again are the vertices of, like, we know that S star only picks these vertices from V0. So these vertices are also not picked by S star. So can you have such an edge if S star was a vertex cover? So this sort of edges don't appear, right? So now what are the other kind of edges that we have to care about? What are the other kind of edges that remain? You could have edges of this form, right? And you could have edges of this form, that's it, right? And of course edges of this form. Okay. So basically just draw all possible edges. So definitely there are no edges of this form. There are no edges inside it. There could be edge inside it, we have to care about it. There could be edge inside it, we have already taken care about it. If there can be edges between these two parts, we have taken care about them. There can be edges, there cannot be such an edge. Now, okay, there can be this kind of an edge, there could be this sort of an edge, this edge and this edge. These are the only possible edges that you can have, okay. Now let's see, what sort of edges would be easy to argue. Let's talk about this edge. What can you say about this edge? Like, for this edge, is this satisfied? Yeah, because look at the endpoints of these vertices. I didn't change the values for these endpoints, so this is definitely satisfied, right? So this is taken care of. Now, what can you say about, again, the same thing holds for this edge, because both the endpoints have not changed the values, so the same thing holds. So what we have to argue about is this edge and this edge, right? Look at this edge. Yeah, look, okay, or okay, look at this edge first, this one, okay? This edge. What can you say about this edge? I have changed the value for this vertex, but I've only added something. So if its sum originally was at least 1, its sum will still be at least 1, right? So this edge is taken care of. So now we have to worry only about this edge. What can you say about this edge? Yes, the value was subtracted but yes, this value has changed. Now here go back to the definition of epsilon. This is precisely why we defined epsilon like that. Go back to the definition of epsilon and try now see the way we defined epsilon. Use that to prove that this edge, like this edge, is still satisfies this thing. So, like when look at this vertex, look at this a prime of v. Can the a prime of v, like, and all these vertices had value strictly greater than half. Can a look at any vertex of v1 and look at its a prime v value. Can the a prime b value drop to less than half? Why? Because of the way epsilon is defined, right? So this value can't drop to less than half. So even in the new a prime v, this has value at least half, maybe equal now, I don't know. And the other endpoint anyway had value half, so it will add up to at least 1, right? So we've taken care about all the edges. So we have actually proved that we have proved that if this holds, then we can give another assignment which is feasible and has smaller size. And hence, if to start with this was the optimum solution, then this thing cannot happen. And hence, this holds.